Okay, here we have to differentiate a product of two functions, both of which are composite functions. So we have a square root, and stuck inside that square root is a linear 4x plus 9. Of course, that's doing some stretching. It's those transformations that typically require our chain rule. So there's our first composite function, and this second function is also a composite because there's a 3 minus x, and that negative attached to that x there, I should say, via subtraction is actually reflecting that power function. So we're going to have to utilize the chain rule when we differentiate the first function and the second function. So let's go ahead and set up our product rule because, of course, first and foremost, this is a product of two functions. So the first function, which I think I will write as a power of a half, instead of the square root. That'll allow us to differentiate that easily. A few more minutes. So first function times the derivative of the second, which I'm not going to bother differentiating anything. Of course, if you're able to, go for it. But for our introduction here to chain rule trapped inside of a product rule, let's just get our product rule set up safely to begin with. So there's first function times the derivative of the second, and then it's the second function multiplied by the derivative of the first function, which again I will write with the power of a half. So that's just our product rule setup. So now let's actually do those derivatives. So rewrite the first function. Just take your time with copying, of course. Don't want any copying mistakes. And now 5 comes down front. We have to differentiate the power function first, the outer function. So maybe we'll stick a multiplication in here. We'll go 5, and then that trapped function remains. And this is to the power of 4 now. And then maybe in a different color, don't forget, a lot of people forget this one. Don't forget to differentiate 3 minus x. Of course, that produces a negative. Okay, so back to our yellow. We'll go to the second half here. So of course I just recopy this. Hopefully I can squeeze all this in here. Now I have to multiply by the derivative of this composite function. So of course the power is what we're differentiating first, the outer function. So half comes down, 4x plus 9. We subtract 1 from that. We get a negative a half. And you probably won't forget this one, but we'll put it in red anyway. Here's our chain rule. Don't forget to multiply by the derivative of 4x plus 9. Hopefully you can see that on your screen, but I guess if I can see it, you can see it. Okay, so that's a mess. Don't be too intimidated by it. Just recognize the chain rule kind of blows that up takes up a little bit more space than you might be used to. So let's go ahead and see what we can clean up. I guess we just have to do these derivatives. And then if you think a little bit ahead, not too much ahead, we got some ugly common factors to deal with here as well, which I think we will do in this video because in the previous video I was showing you some trickier common factors. But first and foremost, let's just do some copying. Enough chit chat. Multiply this by 5, 3 minus x to the power of 4. Okay, and the derivative of that's a lot of writing for just producing a negative 1 there. Of course, the derivative of 3 is 0, and the derivative of minus x is negative 1. So there's our first half, and then we have a 3 minus x to the power of 5 multiplied by a half. 4x plus 9 to a negative a half power. And what does this derivative produce? Yep, just the number 4. Derivative of 4x is 4 and derivative of 9 is 0. Okay, so let's clean things up a little bit. Of course, watch that negative. That's easy to miss. I think we can also clue in that half of 4 is just going to be 2. So maybe be kind of a long-winded screencast here, but you can always fast forward to it. Maybe to be safe, I'll rewrite that out again and do those couple of little minor edits before we proceed with probably the toughest part, and that's dealing with common factors here as well. Get rid of those blotches. Okay, so y prime. So I'm not really doing much other than to say I got a minus 5, which I guess we can put it right out front as a numerical coefficient. And then we got our fractional power in the first half. And I got, of course, 3 minus x to the power 4. Now, if you're able to do some sorting while you differentiate, you can save yourself some copying and possibly some copying mistakes that I'm looking for right at the moment. It looks like we're good. Half of 4 is 2. Of course, I accidentally put another blotch in there. There. Okay, so half of 4 is 2, and that goes out in front. And what else can we do? Maybe I'll write the 4x term first. Of course, it doesn't matter. It's all multiplication. But this might help us get ready for the toughest part, which is yet to come, which is our common factor. So all I did is just clean up, after we differentiated, clean up some of our coefficients there, and I made sure I wrote that negative out in front in that first half so I don't miss it. So now in terms of common factors, don't think there's anything in terms of a numerical coefficient. Of course, I guess you could factor out a negative if you wanted to, but that's probably a bad idea and lead to more sign mistakes. So let's leave our coefficients alone, and let's take out a 4x plus 9 to the power of something. And remember, choose the smallest of the two powers, and of course that is negative a half. So that is the first common factor. And then we have to take out a 3 minus x to the power of something, and we choose between 4 and 5, and of course we have to take 4. So there's our common factor, and now let's see if we can collect what's left behind. We took out all of that 3 minus x term. We still have our minus 5. And then I have to say to myself, okay, what am I going to do with this 4x plus 9? And the nice thing with product rule and quotient rule, you don't have to actually think about this. This should always be 1. It's just the way that it works. So keep in mind, if I multiply this 4x plus 9 by this 4x plus 9, I add those powers, and 1 plus minus a half, Eureka, gives us positive a half. Or this half minus that negative a half power gives us that power of 1. So it's actually not that bad, except you have to watch me do some more getting rid of some blotches here. I will get used to this tablet at some point before end of the year. So now to the second half, we have a 2, and I took all of something out. Yeah, I took out this whole 4x plus 9 negative a half term, so bye-bye. And then we're left with a 3 minus x. This is a little bit easier. We just have a power of 1 in here as well. So when I multiply that 3 minus x to the power of 4 by this 3 minus x to the power of 1, we add our powers. So I'm just looking through here, making sure that I multiply this out, that I didn't screw up my common factor, which is something you probably should be checking as well. So this gives me a power of a half. I got my minus 5, and I have the 3 minus x to the power of 4 intact there. So I just checked out the first half by multiplying it out in my head. Multiplying this by this 2 times 3 minus x gives me 2. That entire 4x plus 9 term, and of course adding those two powers. Bingo. Looks like it's 100% accurate. And now close this thing down. It's in the way. We can start to move some negative powers. I guess just that one negative power to the denominator. So that's going to be 4x plus 9 to the power of positive a half now. So that's looked after. And we're going to have a 3 minus x to the power of 4. And then we got some busy work to do in here, but we do have to expand some things out, which I think I'll do as kind of scrap work because I don't want to copy this all out again. So if I expand this stuff out, I get negative 20x minus 45. And then to the second expansion here, we get 6 minus 2x. So of course, double checking that because you don't want to make some arithmetic mistakes, but it's typically how this plays out when your brain gets taxed with some other things like horrible common factors. But it looks like we're good, and I can simplify that now and write that as negative. Of course, this is multiplication, so I better put brackets. This is minus 22x minus 39. We can get rid of this. Starting to find my way around here, I think. Okay, now the worst part of this question wasn't the derivative. Maybe it was. You might disagree. We have to find out when this derivative is 0 because actually the instructions, which I'm not even sure if I read, is said differentiated, which of course is our first concern, but it also says find out when the slope of this curve is equal to 0. So if you're asking yourself, how do I know how to make this derivative equal to 0? Well, keep in mind you don't want to make the bottom 0, because if you do, your derivative's undefined. So we got some differentiability issues here with this function. It's not differentiable, at least at what makes the bottom 0. And keep in mind there is a square root here, so we will look at the function in a few more minutes. But going through all the trouble of that common factor business actually gives us our answer here pretty easily. It's whatever makes the numerator here equal to 0. And we have two common factors that we've brought out, and one common factor that we brought out, and the other one was a simplification. So those two factors up top, which maybe we'll separate. You get to watch me bumble around here for a few more minutes with this color changes. If we separate 3 minus x, of course, if I make that equal to 0, that's where one of those situations, and I'm not sure why that thing is doing that. Get out of here. There we go. If I can make 3 minus x equal to 0, then 0 to the power 4 is still 0, and that wipes out our whole derivative, and we'll have a derivative that's equal to 0. And of course, that happens when x is 3. So there's one of our two answers, which is one of our common factors. And our simplification gives us our second result, is how do we make a negative 22x minus 39 equal to 0? That answer almost seems wrong with those weird numbers we got. But if I add 39 to both sides and divide by negative 22, we'll get positive 39 over negative 22, which we'll say is negative 39 over 22. So those two x values apparently will produce tangent slopes of 0. And also keep in mind, when we look at our function here with Desmos in a few more minutes, we'll see lots of differentiability issues around this whatever makes our bottom 0, which incidentally we might as well take a quick look at. How do we make 4x plus 9 equal to 0? Just remember, we don't want to. If that's equal to 0, of course that's going to be 4x equals minus 9 dividing by 4. Looks like negative 2 1/4. Okay, so we actually were able to find our two x values for this function where the 0 tangents are located, and of course no way we ever would have got that negative 39 over 22 if we haven't done our common factor process above. So let's have a look at this function in Desmos and wrap up. Okay, so here we are. Here's this function f of x, and you can type this into Desmos and play around with your Windows settings here, but we can see, maybe we can't see. If we click on that, looks like we have a turning point up here, which does have a horizontal tangent, and that's at a negative 1.773 value, and thankfully that is our negative 39 over 22x value that we found, and that is our turning point. And notice what this value is. There's our negative 2 1/4. So remember, the tangent slope doesn't exist there. That looks like a vertical tangent, and of course we also have a big domain restriction there. We have to avoid any x values to the left of negative 2.25 as well, because that would give us roots of negatives in the bottom of our derivative. There's our other value, which of course isn't a turning point here, but our curve does flatten and does have a horizontal tangent at x equals 3. So through that horrible common factoring process, we're able to find both x values where our tangent slope was 0.